So how many people feel very comfortable with the Java memory model? Awesome. That's great. And you know, really as Java developers, this is something we probably should read, but let's face it, I didn't do it for 20 years. So, but I mean, the concurrency guarantees that we're thinking about now are more important than they've ever been before. Just again, usually I give this presentation and people haven't met me yet, but effective Akka, I'm also co-author of Reactive Design Patterns with Roland Kuhn, the head of the Akka team. In this talk, I want to talk about the Java memory model and what it's trying to enforce and what rules it's giving us and tools it's giving us to deal with concurrency. And we're going to talk about what do concurrent and parallel mean. We'll also talk about asynchronous versus non-blocking. We're going to talk about how the heap works in the JVM. And then we're going to talk about protecting shared state on the heap. So again, this isn't going to be a really deep talk with deep code or anything like that. But a lot of this stuff I didn't think about for a very long time. And I thought, you know, I'm meeting a lot of developers who also weren't thinking about this stuff, so why not have a good talk about it? Nowadays we're buying machines with more cores than ever before. For example, there's this new Intel Xeon E5 2699 V3, what a name. It has 18 cores per socket. That's incredible. One of the things I've been thinking about is that maybe it's worthwhile at this point to deploy a JVM strictly to a single socket and leverage just those cores so you don't have inter-socket communication. Yeah, it gives you a tremendous amount of locality. So if you're looking for speed boosts, give that a try. But we really want to deal with shared mutable state in a sane way. And right now we resort to things like synchronized and locking and stuff like that. We might use things like reentrant read-write lock. We've got a stamp lock now in Java 8. But they come with costs. And what are they? So I'm not sure exactly where this person is, and maybe they're even in the room. Anybody know a Juan Pablo Franciscone? No? All right. That actually might be Italian, huh? I don't know. I don't think so. Juan isn't an Italian name. Anyway, he had this really nice diagram on his blog. And I want you to ignore this left-hand side about the method area here. That's not what's important. What I do care about is the heap, which is where Java allocates objects, right? This is our runtime memory space, and it's monolithic in the JVM. By that I mean the entire process shares this heap. And then we have our threads. And our threads, you know, they have an actual implication of cost on the heap as far as size goes. Each thread by default is about 512K in size. That's pretty significant, you know, and this means that the heap is a limiting factor in the number of threads that you can have running on your JVM. That's interesting. But each thread has stack frames, and every time you call a method, it's going to push a new stack frame onto the stack, assuming you don't have inlining, where the compiler or the runtime compiler is going to take what was a separate method and just lift the code right there so that the cost of a stack frame isn't being paid. That's useful, right? Well, let's think about what happens before means. Has anybody ever heard the term happens before? Okay, yeah. This is the guarantee that if you have A trying to happen before B, then the result of A should be visible to B. And think about that. You've got two threads possibly running on the same socket, two cores on the same socket, or they could be on different sockets, right? That Intel machine I was pointing out before had two sockets, each of 18 cores. All right. Well, how are we going to communicate the fact that what happened on A, should be seen by B? And then the other guarantee is something called synchronized with. And the cost of synchronized with is that every time I use it, the data has to be flushed all the way back to main memory from a core. So has anybody ever seen those latency numbers everyone should know? It's that the cost of sending a message all the way to Denmark from the US or something like that. But it also shows to go from a core out to a register, out to L1, out to L2 through the cache pipeline. The numbers actually really weren't that correct, but they gave you a good view of the relative cost. To go out to main memory from a core on a sandy bridge is roughly 66 nanoseconds. That's about 180 clock cycles, maybe 200. It's hard to say because clock cycles don't exactly measure in time the same way. But that just means that you've got to figure out that when you use a lock, you're going to have to push all this data back to main memory every time for visibility concerns and synchronization to make sure everything's visible, all that good stuff. So that's kind of a bummer. We also have something called volatile. Anybody here use volatile? Okay, I'm going to be talking a lot about volatile here. And there's no guarantee of visibility between threads. By pure luck, you may see an update to state on one thread over on another. You may see that happen just by pure luck, but there's no guarantee of it. And in order to get those guarantees, we use things like volatile. So to think about what that happens before implication was, let's think about Akka. Imagine I have an actor. It doesn't matter what it's doing, but it has 10 messages inside of its mailbox. Whenever it's handling messages, Akka has a setting inside of it called throughput. And what throughput does is define fairness between actors. How many messages do I handle before I give up my thread to another actor and let them do some work? Because if I had 1,000 messages and I had no fairness, then I would just process all of them and everybody would be waiting for a thread. So we want some fairness, we want some degree of fairness, but that fairness implies a context switch. We are going to do our 5 messages in sequence, and then we're going to release the thread, and we're going to come off that core, and maybe then the actor is given another thread, and it's going to have to possibly operate on another core, but it doesn't matter, it's a different thread. And that thread can't see the changes that the actor made when it handled the first 5 messages. That would be a problem, right? So everybody understand the implications of that. So Akka actually provides you with a happens before guarantee. You don't have to think about it at all. And I'm pretty sure things like closures, core.async is doing the same thing. Because if you have data being pumped through a channel, that's going to be multiple threads dealing with this, and they have to all be able to see the changes they're making. So that's really important. How would we end up with a case where data did end up being seen by another thread? Has anybody ever thought about cache lines? When you're talking about memory, when you're talking about RAM and the cache pipeline down to a specific core, your data is held in cache lines, and they're typically about 64 bytes. And those 64 bytes, could have multiple variables inside of it. I'm thinking it's supposed to be bit. No, it's bytes. 64 bytes could have multiple variables inside of it, right? So if I do update on my thread a value that is, in my thread, I'm updating it. It's on that cache line. But there's also another variable on that cache line from another thread. The cores have to figure out who's got the right to update what and when. And they do this through a protocol called MESI plus F. Modify, exclusive, shared, and invalid, right? So they're talking to each other through a message passing protocol and saying, oh, I have access to this cache line right now, you're going to have to wait, right? But because these 2 cores are trying to operate on the same, cache line, we get this thing that we call false sharing. And that means that you've got 2 threads operating inside of a single cache line. And they're going to say, all right, well, I'm going to go first, and then you get the cache line. And that means that you may see an update from another thread just by pure luck. You had no control over what cache line that value got assigned to. And really crazy high performance libraries, things like the disruptor, they will go to great lengths to ensure that there will be no false sharing by never allowing multiple variables to be on a single cache line. They will buffer it or use other tools to find ways to get exclusive values on a cache line, therefore guaranteeing that you never have to worry about this cost of negotiating who gets to do what, when. And that's fantastic, right? But not everybody wants to pay that cost and footprint. Disruptor has very specific performance needs, and it's paying a footprint cost and using more cache lines for data to achieve that. So another interesting thing, by the way, is that locks that are contended are actually arbitrated outside of user space. They're at the kernel. And that means that just to figure out who has the right to update something at what time in a JVM, if it's contended, only whenever this lock is actually, two threads trying to do something at the same time, it's going to be a context switch. Because the threads have to come off core, figure out who's got the right to do what, and then they get to execute in order. And that's also another major cost in time, right? So Joe Armstrong has this cute little diagram that he published on Twitter. I'm sure a lot of people have seen this, right? How many people have seen this diagram? Yeah. And the idea was to express the difference between concurrency and parallelism. And the problem with concurrency is that you have something that is shared, and it's mutable, and can be updated by multiple threads. So you have to figure out who can do what when. Joe's example shows, two lines of people taking turns going to a coffee machine. And that means that they're contending on the right to get coffee. But parallelism is when you have no shared state and no coordination whatsoever between them, so they can operate in complete isolation. That's fantastic. Before I move to the next slide, I want to talk about asynchrony and non-blocking, concurrency and parallelism, and I want to give an example. At first I wasn't sure that this was a good one, but people have said it was, so I'm going to use it. I like to wash dishes. Does anybody like to wash dishes? Yay, yeah, all right, woo. Yeah, and I'm also one of those people who, when they wash dishes, I then put it into the dishwasher and, run it again. Does anybody else do that? Oh, nobody else is that crazy. Okay, so I'm a little nutty about this stuff. But, hey, if you don't do that, then you end up with crusty dishes. Who wants that? All right, anyway. So imagine I'm washing dishes there, and I'm sitting there, and I have a process. I'm going to grab a dish, and I'm going to rinse it off, and I'm going to scrub it, and then I'm going to rinse it off again, and then I'm going to put it in the dishwasher. I can't be faster about that. It's a purely sequential process. It's not asynchronous at all. It's purely synchronous, right? I just have to walk the process, go back and do it again, go back and do it again, over and over. And there's no way to optimize that, really. So maybe I think, oh, well, I'll do a couple dishes at once here, and a couple dishes here, and a couple dishes here, and then put them in. I don't know. But it's still going to take, it's like an O of N operation. It's still going to take a linear amount of time. All right, well, say I invite somebody to come over to my house. Raul, you get to come over to my house and wash dishes. Woo! Actually, I'll invite somebody who likes to do it. Yes. So this fellow comes over to my house, and he's going to wash dishes. And I say, all right, you go ahead and wash dishes. I've now spawned work. He goes up to my sink, and he starts grabbing dishes, and he starts doing work. So this is now asynchronous. And if I stand behind him and don't do anything, I'm blocking. I'm not doing anything else. I'm not being useful. And he's probably getting mad at me for inviting him over to my house to do dishes, and he's doing them all by himself. But, oh well. Maybe I decide, you know what, I'm going to go play with my kids, or I'm going to go drink a beer. Now I'm not blocking. I've spawned an asynchronous process, but I'm not blocking on it. There's no concurrency, though. I'm not doing anything that would affect his ability to wash dishes, aside from maybe making him angry. So, okay. So what if we say, all right, well, the more efficient way to do this would be to have multiple people washing dishes at the same time. So we both start washing dishes. And maybe we create a pipeline. And maybe he starts out by, doing the grabbing the dish and rinsing it off and scrubbing it. And then I do the rinsing it off and putting it into the dishwasher or something like that. Now we have a sequential asynchronous process because I've got to wait for him to hand me a dish. That's not very much fun. There's our shared mutable state. I'm contending, waiting for a dish, and if it turns out that there's a pot or something like that that's really messy, it might take a while for him to clean that, and I'm just standing there kind of waiting, not really doing anything, maybe having a beer. I don't know. Anyway, what we'd really like to be is, completely asynchronous, non-blocking, and parallel, so that we spawn work. We aren't wasting threads sitting around doing nothing, and we don't have shared points of contention. Because when we're working together, I've got to wait maybe for the faucet while he's using it. I've got to wait for a dish to come to me, so the faucet, the sink, and the dish are all contention points between us. And we have to arbitrate who's going to do what when. Okay. It would be awesome if my house was so cool it had 2 sinks and we could do dishes at the same time and not share any state. We both grab a set of dishes, we both go to our sink, and we both start doing dishes in isolation with no coordination between us, right? That would be the ideal scenario. Asynchronous, non-blocking, fully parallel, with no points of coordination. Okay, anybody like that? Was that a good example? Yay, all right. And now you know I'm kind of crazy about dishes. So. So I want to take something that Rich Hickey, the creator of Clojure, gave a really great talk years ago called Identity and Value and State. He was talking about time, right? But one of the first things he said in the talk, and I think this was 2010 or something like that, was that he didn't want to talk about it from the perspective of the JVM itself. He just wanted to talk about these concepts at a high level. Instead, I want to sort of take that and apply it to the physical heap of a JVM process. And I don't want to conflate, I don't want to use the same terms Rich did, so instead of saying identity, I'm calling something a name. But then I couldn't think of a better word than value. It's a value, it's a thing, it's a I don't know. See, I can't, so I'm sticking with it. I hope Rich doesn't get mad. He gets mad at me sometimes. Anyway, the name is what you have on the left-hand side of your equals. This is your reference to some value on the heap, right? We say that Java doesn't have pointers. That's a complete lie. Java is full of pointers. It's just they don't want to call them pointers because then you don't get the idea that you can do things like pointer arithmetic. That's what they really wanted to avoid. So 20 years ago when Java first really started coming out, they said there's no pointers in Java. And everybody was saying this mantra and I was like, yeah, there are. So we have our pointer to some value. And, oh, I didn't update this slide, I haven't. Forget it, this isn't compiling code. Anyway, doesn't matter. To give you a sort of representation of what that looks like, imagine that this is the heap. When we create a field in a class, at the top level of the class, we are creating a pointer inside of the heap that then points to a value. Okay. So every time I reference this thing, it's got to look somewhere else in the heap. And the JVM makes no guarantees that these will be right next to each other. There's nothing you can do to say that this value will be right next to the other so you don't have to walk a pointer. Right? Okay. Well then, let's think about it in terms of, a collection. That's where things get really messy. This is an array list. And an array list does give you the guarantee that the underlying array is going to be contiguous in space on the heap. But I still have my name that I see defined here. I define one person, me. I define some person, other, that's my wife. And then I have a list of persons that I'm going to put them into as an array list, right? So I have us here. And I have my array list here containing the array, right? And then I've got pointers going to the me and the other, which then point to the actual values. So when you access a value inside of a collection, you are actually walking a lot of pointers. And people like Martin Thompson hate this. And they say Scala is really bad about it, but you know what? So is Java. Collections are really bad about this on the heap. It's a dynamic of the JVM. There's not much that can be done unless you use very specialized collections. Okay. Well, we could use a method scoped variable, and by that I mean we have a public void my method, just some method, it doesn't matter what it is, but inside of the method I define a variable. And I still have my name and I have my value, but the name pointer does not live in the heap, it lives inside of a stack frame. And that means that you do have an assurance that for every thread executing this method, even though the method has no synchronize, no locking, nothing, they will each see a different person, me, right? Because it's going to live in that thread's stack frame and point to something in the heap, but nobody else has a reference to it unless you somehow publish that out, which would be a bad idea. Okay. Now, we have final in Java, and in Scala we have val. Final is nice because it does stabilize our name. It does say for the left-hand side of our equals that we are not going to have to worry that somebody can change what it points to. It will always point to this instance of person. But that makes no guarantee about the immutability of the person type. And somebody could actually change what's inside of it, right? They could change my name. People do that all the time. So, that's the tricky thing about the right-hand side of equals. You have to think about immutability over here too. In Scala, when you're creating a variable, you have to say whether it's a val or a var. And the reason Odersky did this was because he wanted to ensure that the time you were creating this variable, you were making a distinction about immutability or mutability, because it's very easy to forget to put the word final in front of your reference. And it was so bad actually that one place I worked, I had a save action in my IDE that would automatically put final on everything, everywhere, just to make sure that I didn't forget, because I'm not perfect as a programmer. I make mistakes. So just as a way to help me enforce that, right? Okay, so let's look at the mutability matrix of pain, for which this talk is named. I want to break this down in a couple dimensions. First of all, we have that name, the left-hand side of our equals, right? And that has the var, which is, something that is not final, and val, which is something that is final. And then I want to think about the value. And I want to think about the right-hand side of the equals and whether the data inside of it is mutable or it's immutable all the way down, deeply through its entire, object structure. Because it could contain other objects, right? We could have a person class with an address type inside of it. The address type might have a zip code type inside of it. We want all of that to be immutable, right? So if we're in the space where we are a var on the left-hand side, we have a non-final Java variable on the left-hand side, and we have mutable data, we are in for a world of concurrency pain, because there's nothing protecting neither the data you're pointing to or the fact that you could change what you're pointing to, right? So when you get into concurrency, this is where you really shoot yourself in the foot. And if I have a final value pointing to mutable data, I'm not in much better position. Either way, I'm still in a position where I have to worry that somebody can change the underlying data that I'm looking at. And that stinks. And that implies locks. That implies synchronized width, right? I have to guarantee that the right thread has the ability to change the mutable state or the value that I'm pointing to at the point in time I want, right? So that's no fun. If I have a var, a non-final name, and immutable data on the right-hand side, I'm actually in a lot better shape. Think about this. I can change what I'm pointing at, but the data that I'm pointing to never can change. And this is why, for example, in Scala we have these case classes with a copy method so that you can have completely immutable data types. And then instead of having to create a new instance and pass those values in, you say copy and just change whatever field you want different, right? That way you're always staying immutable. But I can now point to the new value in the heap as opposed to the old one, and the old one is left unchanged. And this implies volatile, right? Because now I have to think about happens before. If I have a new reference that I'm pointing to, even though that data is immutable, I have to make sure every thread sees that I'm now looking at the different field in the heap. Okay. But if I am, and I love this picture so I keep showing it, right? And if I have a val or final data of immutable values, then I am in the best place possible. And languages should enforce this. We see this with Clojure. We see this with Scala. You can write code very easily that is immutable and doesn't have pointers that can be updated. But of course, there are going to be places where you need mutability. So what do? Let's think about the implications of immutability. And this is a real pain point for when you want to do functional programming with everything being immutable all the time. it does require that you're going to use more heap space. So in Java garbage collection, we have our new generation, sometimes called Eden. And then we have our survivor spaces where things that are promoted out of Eden because they continue to live go first. And it alternates between two of them, but that's irrelevant. And then things that survive that collection go to our old gen, right? Where our old generation of things that are long lived inside of our JVM. And one of the things people often say to me is, well, should I resize my new gen and make it larger to take care of the fact that I'm going to create all of these short-lived immutable things? And the answer is really not yes, definitely. Because resizing new gen has implications on performance in the JVM. You are saying that, okay, the one place where I can't choose what collector I'm going to use, and every collection is going to be stop the world, will now take longer. Because new gen is not some sort of, I can use CMS or something like concurrent mark sweep or G1 in new gen. You can't do that. It's not even parallel. So every collection of new gen is stop the world, and now you're telling it to take longer. That's kind of a bad thing. That's going to increase latency on your application. And then there's the additional implication that since you've got a larger new gen here, if you're promoting a lot of stuff, it may not all fit into survivor space, and it may spill over into old gen. And the cost in old gen is now on the stop the world phases of whatever CMS is doing, concurrent mark sweep, or G1. There's also the cost of compaction, because you've had to put stuff into this big old gen space, and at some point it's just like, anybody remember defrag on Windows? Anybody? No? Am I just that old? All right. All right, well, at some point your disk would get so fragmented that you would run defrag overnight or something like that, so compact it all down into one area so that you had space in your disk to put large amounts of stuff, right? It's the same thing goes for old gen, and that's going to be extremely painful. And you can tell a concurrent mark sweep or a G1 collector that you want a max pause time of 1 second. You can tell it that, and it won't listen. So beware. It's nice that they have this flag that actually doesn't really do anything. I'm joking. The JVM is smart. It's a bad idea to interrupt threads. That leads to instability on the JVM. So they're not going to take something that's actually doing something and stop it while it's in the middle of something. They're going to wait till it hits a safe point and then stop it. So it does have some value. It's not guaranteed to happen at 1 second. And if you're counting on that, you're making a wrong assumption. It's really better to think about the effects of tuning GC at various loads. And we sort of see this in Gil Tané is the CTO of Azul Systems. They make their own JVM called Zing. Right? Has anybody ever used Zing? Yeah, it's got an incredible collector called C4, continuously collecting and compacting collector or something like that. And it has very, very minute pauses that you don't have to worry about. You can use this with very low latency, right? Gil has been recently talking about how we're measuring latency all wrong. How many people in the room are on a project where somebody tells you that every message or every interaction with a user has to happen within 50 milliseconds or 200 milliseconds or a second? Anybody have somebody telling them this? I see this a lot, actually. And it's just because we don't think deeply about the implications of latency. It's not that simple. You have to think about it at varying loads. So if I'm handling 1,000 requests per second, 99% of my users will have a response within 20 milliseconds. 99.9% of my users will have a response also in 20 milliseconds. But 99.99% of my users might see 50 milliseconds? Okay. And these are the kind of guarantees I can make across multiple throughputs. I can say at 5,000 requests per second, my 99 percentile is 50 milliseconds. My 99.99 is now like 80 milliseconds. My 99.99 users are going to have a higher cost. A small fraction of my users are going to have a longer experience than others. And you have to do this in multiple ways. You have to try it at 1,000, 5,000, 20,000. Some companies I work with that are really big in the retail space selling consumer electronics. When they release a new product, they might see upwards over 50,000 requests per second, on a single service. And they have to test for this, right? They have to measure how latency will be affected across all these different throughputs. So they understand what their users will see at each percentile. So, you can optimize it if you're that concerned about the performance. But 99% of the customers I work with using Akka, Play Framework, they don't worry about it because the performance is still so much better than what they were doing before, right? Because of the threading model and the ability to leverage all of the hardware at your disposal efficiently, they're just happy. They're like, you know what, a little bit of latency, I'm cool. All right, I can live with that. But volatile is your friend, right? Use snapshots. Use a non-final name pointing to immutable data as much as possible, and then use @volatile. And what @volatile will do is put a memory barrier at the point where that value is updated so that it's published to other threads without any locking, I'm sorry. And because the locking, if it was contended, remember, that would also involve a context switch. We stay in user space. We don't have to worry about that at all. The interesting dynamic about volatile is that if we had 3 fields inside of my person class, like first name, middle name, and last name, and I wanted to update all 3 fields for some reason, right? I wouldn't want to put volatile on every single one of those variables. Instead, I would want to do a group update of all 3 fields and then publish on the last one by having the last one be volatile, right? So I would have my first name, my middle name, and then volatile last name. And whenever I'm updating the fields, because the last one is volatile, all 3 are being published because it happens before. There is an implication on the other side for the people who are going to read these fields. When you're going to read a field that you know involves a volatile, read the volatile one first, and then read the other field. So I would read last name, then first name, last name, then middle name, then first name. Doesn't matter after you do the last name, really, what order you do it, but why not go in reverse order to keep it simple? The tricky thing about this is, if you do this in your code, put a comment there so that anybody else who adds a field doesn't add it after last name. Say there's a suffix, like somebody is a junior or they have a number after their name or something like that. The problem is if somebody doesn't understand that you put volatile on the last field to be updated, and then they put another field after it, and it gets updated after first name, middle name, last name, it won't get published until the next happens before event. So put a comment there saying, hey, make sure you update last name last, or make the other field volatile. Take the volatile off the last name and put it on the suffix. It's your best bet. For greater consistency guarantees, volatile might not be entirely appropriate because, like I said, it's plausible that while you're updating first name, middle name, and last name, another thread does see the updated first name. And if you're deeply concerned about that, then make sure that you use something that gives you more coordination, like a lock. So use volatile. Don't be mutable as much as possible. We all know that this is the best way to write concurrent code. And understand our visibility guarantees, right? Think about the implications of happens before versus locking. And if you want even deeper levels of sophistication for your memory barriers like volatile, volatile is both a read and write memory barrier. If you want explicit read barriers and write barriers, you can go down to sun, misc, unsafe, but there be dragons. That's a place where you can find lots of tools that you could shoot your foot off. So don't just go into sun, misc, unsafe. First of all, they make it really hard to go into sun, misc, unsafe for obvious reasons. They don't want you in there. But somehow they did make it public, and you can find code on the internet to expose sun, misc, unsafe. Just know what you're doing when you use it. Don't just go in there and start playing with everything, right? Okay, that's really it. So that actually is both of the presentations I was giving. What'd you think? Anybody have questions about the JMM, the Java memory model, and volatile or? Yes, again. It's Juan, right?
Sorry?
What's your name, Juan? Was it Juan or?
Sergio.
Yeah, okay.
You meet a lot of people.
Sorry about that. It was years ago in New York, right?
No, it was last year in Berlin.
See, exactly. That's what I said. I'm sorry.
You should adjust the memory model.
Yes, exactly.
Actually, about the memory model, I'm trying to code in Scala in the most functional way possible, which implies using immutable data structures, and also I'm using a lot the case class for the copy method.
Mm-hmm.
But I'm kind of worried about how it affects the memory. I didn't run into any problems yet.
Yeah.
But I have an intuition, that might be wrong, I don't know, that actually it keeps a lot of things as you commented before. So are we secure about using this way of programming, or
yes.
is it somehow optimized by the language itself, by the compiler, whatever? Or
there are minor optimizations in there that the compiler will do. It will try to inline things, and it will try to and this is not just the runtime compiler in the JVM. The Scala compiler does have optimizations in it, but it doesn't have a lot of intelligence about what you're trying to do. So no, we don't count on that, and don't worry about it so much, actually. The only time you really have to worry is when you have a larger heap. Does anybody in the room, Gil today loves to ask this question, does anybody in the room have a heap size larger than 4 gigabytes? Raul, okay, a couple people. How about larger than 8 gigabytes? Just curious. No? Okay. Once you get to 4 gigabytes, Gil calls this the application memory wall. He says that, you know, at 4 gigabytes, you're reaching the point where you are going to have substantial pauses due to garbage collection because of the size of the heap. You know, people who are in the Hadoop space who might be using a much larger heap, sometimes 50 gigabytes. Spark, for example, doesn't even get started until you use 3 gigabytes of heap. Those are going to pay a cost in the time of collection and stuff like that. And for them, they should worry if they had an interactive experience. But Hadoop jobs don't have interactive experiences, so nobody cares that garbage collection took some time in a Hadoop job because it was running for hours anyway, right? Spark, this is going to matter a little bit. I think that there's a real value proposition for using Spark on Azul Zing, because Azul Zing really kicks into gear at about 40 gigabytes of heap size. So if you're going to run a large heap Spark job and you're going to run it on Zing, try it out. You know, just see how well it works, and you might be surprised at the performance improvement you get because you're doing interactive things with Spark where Hadoop you didn't. But for your case, no, I wouldn't worry about it that much. We've been doing this for years, and most of the people out there are not trying to write low latency systems, you know, and they're actually very pleased with the performance they're getting. And by that I mean the largest companies in the world, GE, Goldman Sachs, you know, just about every bank really, the largest retailers, Saks Fifth Avenue, they're all out there using this stuff and being successful. So yeah, believe me, if people were having a problem with this, you'd be hearing about it.
Thank you. Now I'm kind of relaxed about that.
Yeah. Oh, wait, there's a microphone. Where's it? Okay, it's coming.
So, in my opinion, when we tell people that are in the Java world that are used to immutable data structures, the benefits of immutability, immutable data structures, case classes, their concern is always that, you know, you're going to be creating way too many objects to make those copies, so to maintain the immutability. So I know you know a little bit about structural sharing, and I would like if you would explain to people what it actually is and how it actually benefits to have a complete immutable data structure with structural sharing.
Yeah, let me just walk back here into our collection. Okay, so how many people have heard of persistent data structures? Okay, great. How many people understand what structural sharing is? Yeah, the closure guys. Of course. So collections are a really funny thing, right? If you're going to have a purely immutable collection, and think about this, in Java 8 there's a new API called collections dot, right? You can say you want an unmodifiable list or you want an immutable list, and that will give you, the immutable list case will give you an immutable array list. The unmodifiable list will just be a wrapper with no setting mechanisms inside of it, of a still mutable collection. I think that's correct. I could be wrong. I haven't read it that closely. But when you do want to update a list of values, say in this case I've got my list of me and my wife as persons, right? If I want to update that because maybe we've had a child and we now want to add a third element in here, instead of modifying this array list in place, well, I'm going to say it's a Scala list or a closure list or something like that, I then create a new collection of the data. And I reuse the pointers to the values that were shared. Me and other are also pointers in my new 3-element list with a new pointer for the child that we had. So that's structural sharing. And in doing so, threads that are relying on the original view of what my family was are unharmed. They see no change. Now my thread that's operating on the new data has the data it needs in a collection that it wanted with no effect, right? No side effect of messing with the original data. Sort of like that idea of referential transparency I was talking about before. So that's a really fun, powerful concept. And as it gets deeper into collections theory, which is a really deep place to be. Somebody wrote a book about functional data structures. His name was Chris Okazaki, and I think it was for his PhD whenever he was in college. And it's become a really seminal book. If you want to understand deeply structural sharing and functional data structures, I highly recommend you find his PhD thesis out there. You can buy the book, or you can not pay him and download it on the internet. But I think there's a white paper as well you could read. But it is a good concept to understand that you're just copying the pointers, not the values themselves, right? And that's where on the JVM heap you get a real win, right? So, any other questions? Ro, did that express it really well?
Yeah.
Good. Okay. Yeah.
Okay, I'd like to ask if you know the memory model of Erlang, and if you think what's your opinion about having multiple garbage collector for each actor?
Yeah, sure. I can't say that I'm an expert about this, but I have a fair amount of knowledge about it. So in Erlang, the language has its own VM called Beam, B-E-A-M. And it has the ultimate level of isolation, right? So by that I mean every single actor in Erlang, just think of it, every single class, has its own heap, unaffected by any other heap. And what goes wrong in that heap does not affect the other actors, right? So if I want to send a message from one actor to another, it's got to copy the memory out of the heap from the calling actor, put it into the message, and then put it into the heap of who received it, right? So you have absolute isolation. But this is also one of the reasons why Erlang isn't particularly fast at execution time. Don't get me wrong, Erlang's still a fast language, but it's not as fast as it could be because of these prices you're paying in footprint to guarantee complete isolation. It comes with some caveats. So think about this. In Erlang, you have something called selective receive. And by that I mean, I receive a message. If I don't handle that message, I put it off to the side. I receive another message. I also don't handle that message. I put it off to the side again. Then I receive another message. And I do handle this message. And remember, I was saying earlier that actors, whenever they get a message, they can switch what they do. Okay, well at that point Erlang is going to look at the messages that were in, that stash off to the side, and it's going to replay them and see if they can be used now. And if they can't, it puts them back over to the side. Is that correct? Yeah. So every time I successfully handle a message, I am increasingly handling more old messages that are building up over time. And when an Erlang actor runs out of memory, that is like an out of memory exception on the JVM, except because of the isolation of the heap specific to that one instance, you don't have to worry that it affected the other ones, right? That's great, but we can't do that on the JVM, right? This is actually the fundamental flaw of the original Scala actors. Philip Haller was a doctoral student at the EPFL who wrote the original Scala actors. And interestingly, his PhD was about, what do they call that concept in Rust? Gosh. Rust has this publishing or something like that mechanism that Philip Haller was actually, a really instrumental person in figuring out. We just never put it into Scala. The implications of doing selective receive, which the original Scala actors had, was that every message that wasn't handled was put to the side. Every message that wasn't handled, put to the side and replayed, right? But that's a memory leak. And we have a monolithic heap. We don't have separation by actor. So it is a mathematical certainty, unless every message is handled in an actor on the JVM, that in time you will run into an out-of-memory error. There's mathematical certainty, you just don't know when it will happen. And we saw this. I was doing Scala actor development in 2009, 2010, and we did see this in production. Akka took a different approach. Akka said, all right, well, I'm going to receive a message, and I'm going to give you the choice of what you want to stash, what you want to put to the side. So you have to explicitly say, take this message, put it to the side. And you also don't pay the cost of replay on every handled message. You get to say when to replay those messages. Now I want them, right? That's nice. But the implications, Erlang is by far the most resilient language out there. They say they have 9 nines of uptime verified. And by that they mean in 100 years, they only have 3 minutes of downtime, I think. 3 minutes of downtime per 100 years. That's pretty hard to top. Their fundamental focus was building something completely resilient. And they've become the model for how everybody should do it in systems today. So, does that answer? Okay. Probably a lot more long-winded than you wanted. Okay. Battery's dead? Okay.
Hi, Jamie. Juan from New York City.
Okay.
2 years ago.
Oh, it was you. I'm sorry. Sorry about that. It's been a while.
When I started to write Scala code some time ago, I, of course, was out of my mind to write a bar. Okay, bar was as hell, and after reading the Martin Odersky book, well, mutability was the way to go, and this was a very good slogan, and I think that it was right. But then I ran into a problem, and it was that coming from a Java world, I was used to think in terms of inheritance hierarchies, okay, and extension and so forth. So immutability doesn't get on very well with inheritance, especially when you are writing generic code.
Yep.
You are at a generic level, and you have to write, you have to create an instance of a generic class and you don't know the constructor.
Yeah, and you get into initialization order problems, yes.
Yeah. So what do you think about the relationship between these two features, immutability on the one hand and inheritance on the other hand? Do you think that in order to go along with immutability, you have to get rid of inheritance and use type classes? Or
No, I think you just have to understand the concepts of initialization order inside the JVM. So in Scala, with a trait or an abstract class, a trait being like a Java interface, say, right? You can define a val. The problem is that you have a class that is going to either implement that interface or extend that abstract class. And there's a rule on the JVM that superclasses are always initialized first. So that val is going to be stabilized in the abstract class or trait before you could actually assign it in the class that's trying to do something with it, which of course blows up, right, in an ugly way. We have, compiler time checking for this. You do see a warning saying, hey, bad idea. But I don't think this is something I want to completely take away. And the reason is, while I'm not a fan of inheritance, I am a fan of extending my classes by the dynamic implementation of extra traits. Right? I don't like abstract classes very much. I try not to use abstract classes at all. I do like traits. And in Java, we have this now in Java 8 with defender methods inside of our interfaces, where we can have an implementation for a method that is the default implementation that can be used or overridden. So you don't have to rewrite it in all these different places, right? I want to be able to assemble a type, right? And by this I mean the example we give in our fast track to Scala class is, you know, I have a bird and a bird can fly, and I have a duck and a duck can, or fish, a fish can swim, right? Well, what happens when I have a penguin? I can't extend the functionality of being a bird that swims without duplicating code. And we get into these rigid inheritance structures when we try to do, you know, non-compositional inheritance. Instead, if we treat interfaces and traits what they should be, characteristics that are bolted onto a class, and instead of saying that I'm a bird or a fish, I'm saying I'm a swimmer, I'm a flyer, right? And I have behavior as a result of that. I'm an animal with a beak versus a duck bill. I have webbed feet. You know, by assembling these kind of traits, I can create a platypus. And I like that. We've known that inheritance is a bad idea in Java. At least, somebody told me this for the first time in 2000. And I was like, nah, come on, that's not true. But then I started doing it for a while, and I realized they were completely right. We know that we want to compose types. We don't want to, you know, build these rigid inheritance structures. So I don't want to get rid of inheritance, but I also don't want to use inheritance the wrong way, right? And there's no real, maybe it would be better if there was a way to say at compile time, hey, you're creating something really rigid and ugly here, but that might be more intelligence than a compiler can really give you. I don't know. It's tough to say. Did that answer it? Okay. Does anybody have any questions in general about Typesafe or what's going on in the world? I said something pretty inflammatory to some Scala developers just last week. I said that Typesafe is not the Scala company. I said it's the reactive company, which of course makes everybody think about me being some marketing person, right? Typesafe is not the Scala company. Scala is owned by the EPFL, not Typesafe. We build a compiler for Scala. So people could say, well, all right, then who owns Scala? It is the EPFL, and it is their jurisdiction to define the role of where Scala will go, right? And Typesafe merely tries to make an enterprise class compiler that large corporations can know they're getting, you know, a bulletproof implementation. And that does not mean that we don't like Scala or love Scala or want you to use Scala. Of course we do, right? It's crazy to say otherwise. But at the same time, we're trying to let people know that we also are okay with them using Java. So for example, Akka and Play Framework are completely compatible from a Java API. So I would say more than 50% of our users from both Akka and Java, believe it or not, Akka and Play are Java users, more than 50%. And that's surprising, right? But look at what an organization, a big bank or you know, a large company. Apple has at least 5 projects. They have 5 individual contracts with us. And by that I mean support contracts, right? I can't say what they're doing. Some of them are obvious if you look at the jobs on, you know, the Apple website. But 3 of those groups started out using Java. There's an inevitability to Scala, and we are cool with that. We know, and I don't want to upset Java developers here, but it is coming, and the Java world can't stop it. And the reason is Spark. Spark is completely changing the dynamics of languages right now, because now companies have a very important business reason to use Scala exclusively, right? You could use Python or R. I know I'm upsetting the closure guys, I'm sorry. But let's face it, Databricks is not making any effort whatsoever to support Clojure directly inside of Spark. I'm sorry, it's not my call. That said, Spark's usage of Scala, because it's implemented in Scala, is driving the ability to use Scala with it better than Python. So before the data frames implementation in Spark, the cost of using Python or R was 3 to 10x per interaction, because it had to serialize a function, send it out over the wire to wherever the data was, and then it had to deserialize it, and then spawn a process and run this code. And even with PyPy or whatever C native implementation of Python that was being used on the other end, even with that, it still couldn't come close to the performance people were getting with Scala. So the kinds of people who are coming to us and talking to us about Scala, the companies, these are the same companies who said, I'm not ever switching to Scala. But now they have to. And we think that's great. You know, there is a really, it is inevitable. And we no longer have to toot its horn. We no longer have to yell, Scala's better or anything like that. People are seeing it. That's kind of fun. Yeah. Another interesting thing, did anybody see Myriad? This is a framework that just came out about a month ago. It was developed by MapR, which is one of those big data companies, and it was developed for eBay with Mesosphere. So these three groups got together and they broke down the wall between your Hadoop cluster and your application cluster. By that I mean, the old Hadoop cluster that you built was a bunch of machines that couldn't be used for anything else, and the resources were negotiated by something called Yarn, right? And Spark runs fine on Yarn, that's great, it'll work. But for your application tier, if you want to use that same kind of resource negotiation, you're going to use something like Mesos. Anybody here ever use or hear of Mesos? Yeah, it's a really great tool for abstracting over all the machines you have with all the different things you have to run on it. I've got to run Oracle, I've got to run Cassandra, deploy it out into all these machines, I don't care where. Maybe a good idea, maybe not for some things. I probably wouldn't do this with Oracle, but maybe for Cassandra it's fine. Because Apple is using, and this is published information, you know, a 75,000 node cluster of Cassandra. And they're building a second one. And, you know, that means that they're running it on top of Mesos, so that they abstract over the machines that they're going to be on. The point of this is that Myriad is a tool which is going to do resource negotiation through Yarn for Mesos. And now the two clusters which could never interoperate can be one. All of those machines can be used for a single, like, abstracted set of resources that can be used. And that's mind-blowing, right? How it works is you have a request for, I need, I don't know, 4 cores, I need 2 gig of RAM, I need so much disk. And then the request goes to Yarn. And Yarn says, all right, I'm receiving offers from Mesos that say, I've got this much RAM, this much, this much cores that you can use, and this much disk. And when it accepts an offer, it then gives the work to Mesos to go off and spread that around both clusters. And then Mesos reports back to Yarn. So Yarn is doing nothing more than bookkeeping. This is going to be, I think, the biggest change in big data processing that we've seen since Spark came out. Because now you don't care that you have separate clusters, you have one. That's big. And think about the implications here. Now you can write applications that directly leverage your big batch Hadoop-like data. Wow, that's pretty crazy. So, cool things happening. Anything else? I hope I haven't upset the Clojure people too much. I'm sorry. Yeah, on.
Okay, with about the Scala ecosystem, Typesafe, you have done a great work. Helping to grow the Scala ecosystem, and you have Spry and Sleek and many other frameworks. Is Typesafe helping to grow the Scala ecosystem further through new frameworks, or
is Typesafe doing what?
helping to make other frameworks for the Scala ecosystem?
No. We had nothing to do with Spark. We had nothing to do with Kafka or Samza. These are just amazing things people build. Another reason for the inevitability of Scala is look at the things that people are building with individual languages, and it tells you what they can express with a language. Yeah, Scala is, people say it's complex because there's all these different ways you can do things. But you know what? You also aren't limited in your imagination for what you can accomplish, right? There's Shapeless out there, which is this mind-bending tool for figuring out heterogeneous data, data of all different kinds of types, and saying, I just want to handle the integers inside of it. That's crazy. And it's doing really nutty stuff, but you could only express it in a language that doesn't have the guardrails, the barriers that prevent you from expressing your imagination, right? It's a great idea to have a language that tells you prescriptively exactly how you do everything, but then you become locked in the mindset that that's the only way I can do something, instead of thinking about a problem and saying, what if I could just do something in a really great, cool way that nobody's ever done before? And it's resulted in these incredible tools that we had nothing to do with whatsoever, right? I mean, we were sort of like that at the beginning. The only reason you could do something like Akka was because you didn't have the rules of Java in how this thing was built. Even though there's a pure Java API for Akka, underneath the covers, it's mostly, Scala. So it's harder to do in Java. So yeah, we're just really happy to see people doing this stuff. We end up partnering with some organizations, like the people who created Kafka, Jay Krebs and Neha Narketi. They have partnered. We haven't officially partnered yet, but we collaborate a lot. But we have nothing to do with Kafka, right? We just talk to each other about the companies we see using each other's stuff. Databricks, the people who do Apache Spark, we have a partnership with them. Mesosphere, they built Marathon, which is a really great tool in Scala. We partnered with them just because we all have common concerns. You can see a stack developing right now for successful distributed systems on the JVM. And it involves tools like Kafka, Spark, Cassandra, Akka, right? These are becoming ubiquitous in large data processing. And just about every client I talk to is using them. So it's pretty cool to see because they work. Yeah. I know that sounded like a big infomercial, but what can I say? I talk to a lot of Scala developers, so yeah. Anybody else? Anything at all? Did everybody get the stickers? Anybody who walked in late? We have stickers on the desk here for Akka, Play, and Scala. Typesafe if you really want one. An interesting point, and mind you, this isn't necessarily something I'm going to guarantee is happening, but somebody asked me this question last week. What about a foundation for Scala? What if Typesafe wasn't, considered the steward of Scala? And we said, we've actually been sort of working on it in the background. This isn't a formal announcement of something that's going to happen for sure. It's a hard process to put in place. And let's face it, this has been screwed up before. Remember the open source foundation? That was a massive, colossal screw up trying to prevent the major vendors in, Linux from, screwing up the ecosystem. But it didn't work. And you can't have political infighting in this. If Typesafe is going to be involved, we have to be another person on it just like anybody else, including the people from Type Level, including maybe Twitter and other major stakeholders of the language. So hopefully, sometime soon, we will see Scala become a foundation and not affiliated with EPFL, not affiliated directly with Typesafe. We're just part of the community that's helping to guide it forward. And wish us luck. I mean, this is going to be hard, and I'm sure we're going to screw up in some way that people are going to tweet about. But it's not because it's of malicious reasons. We are only trying to, help the community express what they want in the language, while at the same time try to make it as bulletproof as possible for the enterprise. Because that's what pays for all of this open source stuff to be free for everyone else. Yeah. Does that cause any questions? Okay, well, thank you.